Okay, thank you for the lovely invitation to this beautiful place and for the beautiful conference. And everything I'm going to talk about today is joint focus door elbowing. Okay, so let me start by defining the model. So I won't be defining easing in this talk. I hope it's okay if there's one talk where easing is not defined, but I will define the model I'm talking about. So this is just a random walk with memory, and the model is very simple. So you start a water. Let me draw the picture in 2 dimensions, though we will be more interested in high dimensions. And you write one on every edge. And okay, you look around you see 4 ones, you normalize it to probability, so that's quarter for every step, and you walk in that step, say in this. All the initial weights are 1, but once you have traversed an edge, you increase the weight of that edge. There is a parameter called A, which is positive. And if the walker starts here and does the first step here, now it's here and it sees 1, 1, 1, and 1 plus A. It normalizes this to probabilities. So the probability, for example, for going up would be 1 divided by 4 plus A, now not by 4, while the probability to return would be 1 plus A divided by 4 plus A. Okay, so that's the model. I think it's pretty simple. Let me just, so the weights, they're going to be 1 plus A times the indicator that the weights of an edge that the walker traversed that edge in the past, in either direction. Cool. Okay, I hope it's not too small. I'll try to write big. Okay, so is the definition of the model clear? Yes, let me. Yes, in either direction. Okay, any further questions? Okay, I guess that's clear. And for the history, I'm going to also discuss another model. The topic of this talk is once reinforced, but there is a related model called linearly reinforced. Linearly reinforced random walk, which is defined in a very similar manner, except the weight is 1 plus A times the number of traversals. So while in the once reinforced, you just increase this to A and that's it. It stays at 1 for A for all times. In the linear case, if you decide to walk that edge again, you introduce to 1 plus 2A, and then 1 plus 3A, and so on. Okay, is the difference between the two models clear? Okay. So let me talk a little bit about the history. The linearly case was the first that was studied. And how will I do it? Let's say, and this started from works in the 90s, not in the 90s, in 1980, by Diaconis and Friedman. We started exchangeability. Let me not define what is exchangeability or what they studied it for, but their study led pretty naturally to linearly reinforced random walk, and so the question appeared: how does linearly reinforced random walk appear? And the first result of that was from '88 by Pimentel. Now I never remember if the L is before the E or after the E. And what he did was the linearly reinforced random walk. I will always use these abbreviations, linearly and one, so get used to them. On a tree. And he showed the phase transition. So you are probably wondering in which parameter. Of course, there's only one parameter here, A. So he shows the phase transition in A. And the behavior is quite interesting. So if A is bigger than some critical A, then the walk is transient. In the case of it, since it's a tree, even ballistic. Basically, it doesn't look much different than a random walk. It's not the same, but it doesn't look much different. Well, if A is smaller than the critical A, the walk is actually not just recurrent, but even positively recurrent. So what does positively recurrent mean? It means that, in fact, you spend a constant fraction of your time at your starting point. Something that you don't get for simple random. So just depending on A, of course, but the opposite. So this is the so the larger A is you spend the bigger fraction of time, but this is there is a constant which is a fraction of random. There is a random constant such that for all time you spend a fraction of your time at your starting point. This constant is random. It's not it's not a deterministic function of A, but as A increases, the constant becomes, the distribution of the constant becomes closer and closer to. That was pretty interesting. And after that came a long hiatus in progress. People assumed that the same will hold for ZD. But there was a long, at least for D bigger than 3, and that for D equal to 2, it would be recurrent for all A. But there was a long hiatus and not much happened. And once enforced appeared during this time as a kind of toy model. And I think for a long time it was considered just as a toy model. So the first result on once enforced was in 2001 by Duret, Trishen, and Limits. And they did once enforced random walk on a tree and found that there is no phase transition. So for any value of A, it just looks like random walk. It's ballistic, and that's so. And this was not completely easy because as A becomes a larger, you need to work for A large, but they worked, and that was the result. And people assumed that this is also what happens on ZD. So I guess somehow, so that's why it was pretty surprising when around 2009 or 10, I don't know exactly when, Vladas Sidorovicius made the conjecture, not the result, that once reinforced random walk on ZD has a phase transition. And the phase transition is a little different from the phase transition for linearly reinforced. So this is the linearly reinforced case. And for the once reinforced random walk, he conditioned a slightly different picture. So A smaller than AC, you again, okay, D bigger than 3. You are again transient, but of course not ballistic. That's easy to prove that it's not true. While for A bigger than AC, you are recurrent, but not positively recurrent. You return to your starting point after time. Okay, and in fact, okay, W will always be used to denote the process. So W is the process. So W is or process. And if you look at the set, not at where it is, but the set of, say, sites visited up to time t, then this is more or less, in some sense, well, it's a conjecture, right? Some fixed convex set times t to 1 over b plus. Okay, so the picture that Vlad has conjectured is a kind of a growing balloon. That you have a balloon that grows quite slowly, and the random and the once reinforced process is jumping inside this balloon and getting to all points more or less equally at equal time. So about in particular at 0 it spends like t to 1 over d plus 1 of the time. Up to time t it spends at 0 something like t to power 1 over d plus 1. Yes, Bernie. Probably, but nobody can prove anything. So, but yeah, you would assume that. Yeah, you would assume. Okay, any questions about Vladis's conjecture? Yes.
Would you also expect the center point of this convex shape to like wiggle or not?
Probably not by much. Probably only constantly. Yeah, it's a bit like, yeah, no, in similar model it only wiggles by zero. Okay, any further questions? Okay. So this essentially finishes the historical introduction, except just to say that the linearly reinforced was thoroughly analyzed in around these years by well, okay, this is somehow when the papers appeared, but this was a long process by many people. Essentially, almost everything is known about linearly reinforced. It does have the same behavior with a transient behavior for, there is the single critical value. There is it's transient for d bigger than 3. Above that critical value, below that critical value, it's positively recurrent with exponentially decaying retainment times. Dimension 2, it's always recurrent, etc. So essentially, almost everything is known. There remains the question of the existence of Bern, of a BK transition, but this is not it. Okay, so questions about the history of the two models?
Now it works. Okay. The behavior is the same. Is the same conjecture. I mean, this for the linearly reinforced. It's you have the same shape, kind of shape theorem with the same exponent, etc.
It's not. There is no inflating ball for linearly reinforced. It's positively recurrent.
Ah, you said positive. Okay, I didn't hear. Okay, thanks.
So it's not the same behavior. It's positively recurrent, which it's trivial to show cannot happen. Okay. Okay, so now I can state our results. And we actually put it, okay, well, we put it on the archive the beginning of the year. And this is basically the first result for once reinforced random walk on ZD, at least for D bigger than 1. And we show for D bigger than 6 and A sufficiently small that it's transient and has a CLT, which you don't actually expect, I think, for linearly reinforced, but maybe you do. In some sense, you do. Okay. So that's the result. Okay, so that's all I had to say about the result. So if you want, I can start. Yeah, question. Yeah. That in the usual sense that if you look at the process at time t, divide by square root t, then this converges in an appropriate topology, in a Wasserstein topology, I think we can even get it. Yes, certainly. Some Wasserstein topology anyway, to a normal variable with some bias, which depends on A. Yes, the whole thing is symmetric to rotation, so you cannot, right? It must be. I mean, symmetric to coordinate coordinate permutation. So there's no other matrix. No matrix is symmetric to coordinate permutations except scalar ones.
What do you mean by AC? Because you don't know the other.
Oh, right. So I will write A0. We don't know the existence of a second phase, and therefore we don't know the existence of a phase transition at all. We don't know, and then therefore we can't even ask if it's unique. So for A sufficiently small.
Hello.
Yes.
Anyways, this is the comment from Sebastian Martino from the Zoom saying that people on the linearly reinforced random walk include Sabotae and Zheng Udaman.
You know, the list of names is very long. This was yes, Christophe Sabot, Pierre Therese, Zheng, but also Margarita Di Sartori. It's based on all the work of Tom Spencer and Martin Zierenbauer. And then there is also the work of Nick Crawford and Omer Angel and myself. So, you know, there are too many names in a list. Okay, any further questions about the history of the result? So let's start the proof. Okay, so I will not try to fit the whole proof into the talk. It's much too long, but I will give you some ideas, and hopefully it will be at least a little bit. Okay, so let's see. So what do we want to show? We want to show that it looks, CLT is here the main point. The transients we get as a corollary of everything that's going on. So the idea is an induction on scales, of course. Assume lots of people here. Let me say induction on time. And what we are going to show is that if we are going to have an induction assumptions that say that the walk looks like random. The induction assumptions would say that it looks like, let's say, Brownian motion for all t smaller than t. And we will just prove that the same thing holds at t, and then the induction will be complete. Okay, so this is a general scheme which has been used for in many ways. In a way, even Lace expansion is like that, at least the way Bridges and Spencer originally proved it. But of course, to make this, but I have to tell you the assumption. Otherwise the whole thing has no context. So let me state for you the assumptions, not completely precisely, but sufficiently precisely for now. So then induction assumptions. What are the assumptions? There will be two assumptions. So assumption one or H1, like we call it in the paper, is that the probability that the process is in any given vertex at a time t is smaller than t to minus d half, which is what we expect for random walk. And then we take we want a little bit of leeway, so we add a small constant. Okay, so that's, as I said, the assumptions of the type. The process looks like random walk, and this is a relatively a simple behavior of random walk type. For random walk, at every time t, this is more or less correct, except if v is too far, and then there is exponent. But this is just an upper bound, so it's true without this leeway. We are assuming that it's true with a little bit of leeway. Okay, so I think this assumption is pretty natural. The second assumption, which is also natural, but it will take a little bit more definitions. So for assumption 2, let me first define a good block, a good block. So lambda is a good block if what? If lambda intersection the whole path. This is, I'm still using this notation as I used this before. The path that the process does up to time t. So all the vertices visited up to time t. Well, what do you expect? Well, okay, maybe I will call it, no, I need an, okay, so lambda, let's call it lambda r, right? It's a block of size, of tide length r. So for random walk, you expect r square visit at most. And again, we will require something similar, but with some leeway. So that's a silly mistake in my notes. Okay. So let me be again and again. I will need more leeway for this one. So let's make it 2.5, and maybe even I will increase the leeway later. Okay. So that's the definition, and again, you see this is in the style of what we'd expect from random walk. And then a relaxed time, what is a relaxed time? Then I'm continuing the definition. Is sometimes, so t is a relaxed time if okay, so this is a definition. So let's see. So what we want, okay, maybe it's a, maybe I'll do the picture here. So what we want is that when we look at the tip of the walk, then in any square, small or large, you're smaller than, you're good. You haven't spent too much time. If it even spends in a small box too much time, then that's not a relaxed time. Okay, we need it at all scales. So of course, even for random walk, not all times are relaxed. So we have to be more modest than requiring that all times are relaxed. And here is the now I can state H2. Not the exact statement as in the paper, but I'm still hiding a nasty thing under the carpet, but you will forgive me. And so assumption H2 is as follows. The probability that for every, did they call it S in my notes? Yeah, sure. No, so let me put it like that. For every t smaller than t, the number of relaxed times in between t and t plus t to the epsilon is at least 0.9 of, let's say, of the size of the interval. So 90% of the points are relaxed. I don't require all of them to be relaxed. I require 90% of them to be relaxed, and I need it everywhere. This probability has to be extremely large, so super polynomial, let me put it like that. And epsilon is again a fixed number. Let me put it here because it will repeat. So epsilon is just 10 to minus 4. Yeah, let's, no, here I should put, no, yes. Right. And here I should, yeah, right. Sorry about that. Okay, so that's the second induction assumption. So again, this is what you expect for random walk. In fact, for random walk, it holds with probability probably e to minus t to the epsilon, but I'm not going to be, what I care is that it holds for super polynomial probabilities, because super polynomial probabilities can be summed easily on all scales. So this is it. So these are the induction assumptions. Are the induction assumptions clear? Yes. This is the assumption that yes, H1 for every t smaller than t, and also H2, which is this, for, well, maybe I should write here -1 or something. Yes.
I have a question. What if we take R equal to 1 or 2, something like this?
Yeah, that's what. So you're right. R bigger than some constant, which. No, you're right. To get 90%, I should have asked R bigger than some constant. Otherwise, you're right. The constant is something like 10 or something like that. It doesn't depend on A. But it's just some constants that should random walk will already have this property, and then this works. Otherwise, you're right that I have. So in the microscopic, we give in the microscopic scale we need to. Okay, any further questions? Okay. Okay, so we have these beautiful assumptions, but you need to show that they are preserved. And the proof has two parts. One, which I will not detail too much for two reasons. One is that it's mostly similar to how it was done in the previous paper of Doe and Ellen Sly on the interchange. And for the other reason is that I talked about it in Geneva, and there must be at least 50% intersection between the audiences. So okay, so we need, so starting, now we start the proof. So first step, you conclude lots of good properties of Brownian motion-like properties. The general scheme is more or less intuitive, because if you see, if this is T2 minus D half, and if the path is not very thick, and you hit every point with probability rather small, then you can just sum of them and get that with pretty large probability, you don't hit your path. If you don't hit your path, you're independent from it. Then you can use all kinds of results for independence. It does contain quite a number of tricks, which are interesting, and I like them, but I will skip them. So I'm going to completely skip the first part, the first element of the proof, which is how to conclude from those two properties, CLT escape probabilities from lines and balls and so on and so forth. Let's agree that whenever I say that something behaves like random walk, you will believe me that it follows from these two properties inductive. So now we need to show that these two properties, in particular H2, holds for longer time. And that's where there will be some, we will need to work a little, we will need to work more. I would also, yeah, okay. So we need to show property 2 at a longer time. We need to show that, again, with relatively high probability, all blocks, or for most of the time, you are in good blocks in all scales. So this is most of what, by the way, how much time do I still have? Okay. Okay. I'll maybe remove 5 minutes for lunch. Okay. Now, okay. So we have, so the crucial parameter here is R, because we are studying blocks in various R's, and we need the proof. We need different proof for different scales of R. And in fact, so we will give a different argument for R bigger than R to some small power, and for R smaller than R to some small power. We'll give completely different arguments. This is the last magical number, I promise. Okay? And I'm going to talk mostly about the case of that R is bigger than R to the delta. Okay? So we have some scale, 10 to the minus 5. We are looking at boxes bigger than 10 to minus 5. We want to show that the process is good in these blocks. And here's where the capacity argument goes in. The capacity argument is the newest part of the proof. So I think this is worth describing in most details. Okay, so capacity. Okay, so I think you've, yes. R bigger than T to the delta. Thank you. Any further questions? So again, just to recapitulate, we are looking at R at mesoscopic scales, not too small, but still quite a large sequence of scale before it comes trivial at something like square root T. And we need to show that the random walk does not, that the once reinforced does not spend too much time in any such block. Okay, so capacity was mentioned in Pierre-François' course, so, but let me still define capacity because I'm not sure we use the same definition. So for me, the capacity of a set, okay, is just the sum over all the points of the set of the probability when you start from that point to escape. This is a random walk capacity. This is the usual capacity, to escape A. Well, escape A means simply that random walk okay, I'm using R for random walk, right? W is the process, R is just simple random walk of the type we all like. Does not intersect it. Well, okay, this is just the escape, not the probability. This is the event. Okay, so this is the event of escaping from. Okay, and the capacity is defined as the sum of these probabilities. Okay, the definition of capacity clear? Okay, great. So this is a classical object, but what we'll study is, of course, the once capacity, the capacity with respect to once random walk, which we define in a similar way. Yeah, here it would R, here it would be W. Like the once reinforced random walk escapes from A. Okay, and this is a little bit more complicated. For technical reason, but I think it's not worthwhile to discuss this complication. So the definition of escaping is a bit more complicated, but I don't think we need to just think about it as something similar. Okay, so this is just the definition of one's capacity, and the proof, therefore, we will show that A, one's capacity is small, and B, that gives a bound on the volume. So let's start with why should one's capacity be small for a typical block? Not for every block, because it will happen with okay, so step, they already use the word step. Okay, so 1A. Oh, so say 2A. I want to show that the typical one's capacity of the path of the one's capacity itself, intersection some box of size R, is smaller than something. And I will immediately tell you what it is. More or less R squared. Okay, and this is a rather simple argument of the form, if you try too many times something with high probability, then it will happen. So let's see how that goes. So, okay, so fix P bigger than 0. And now I'm claiming the following. The probability that the number of P smaller than T such that if you were to start a random walk, well, okay, First of all, WT is in lambda. And then if you were to start a random walk, an independent process from where you are now, then the probability that it would escape your past is bigger than P. Okay, I will finish writing this and then I will explain because this is, I don't want to stand too long. Okay, so what is this beautiful formula, which is all the proof of this step, saying? You look at times, you have been walking and walking and walking. Finally, you are in our box of interest because the process goes in and out, but you are at some time that you are in that box. You look at your past and you say, what's the probability to escape this past? And I'm saying, suppose this is an event on the past. So I should probably have put here conditioned on the past, if you like. This is an event on the past. But maybe it doesn't make more sense to put this here. Okay, maybe this is just, so this is an event on the past. The past is such that the probability to escape it is bigger than P. And now I'm saying, suppose there were too many such things. That's not possible. Why? Because if the past is such that the probability to escape it is P, and you try it lambda over P times, then you would escape with probability E2 minus lambda. Right? You cannot have something if the probability that you actually escape is bigger than in fact, the process, rather than an independent copy escapes, is bigger than P. And if you try something lambda over P times, which has probability P, then you will succeed with probability E2 minus lambda, 1 minus E2 minus lambda. Yes, so, okay, the way it's written, if you failed all of, you can fail all of them only with probability E2 minus lambda. So this is just this kind of argument. And the R square here is because you only know that you didn't, and of course, if you escape, then you are not coming back. Okay, so the R square here is only because you only know if you escaped or not after more or less R square times. So you only really have independent trials only after R square times. That's what there is an R square. So this is essentially the proof of 2A. There will be a few, 2 or 3 more lines, but that's the argument. Is this argument clear? Questions? Already, I guess people are still digesting this. That's why there are no questions. But again, so okay, maybe I should just put it. Okay, so it requires a little bit of digestion, but it's really a standard argument. Okay, now let's finish once you've agreed to that, there is not much to do. So you use that with lambda equal to log cube, right? You need spares, right? You need to increase the probability from step to step. So you use that with log cube t, so you get the probability of the same thing, but with this lambda equal to e minus c log t cubed. Now you just notice, let me only copy the W of 0t of all this formula. And now let me notice that if this holds, then I can replace this with the walk until the end, because that just decreases the probability, right? Because if it can't escape this, and it certainly cannot escape an even bigger set. Okay? And now you sum over all p's, but this is the, okay, sum over p. But of course, in exponential scales, you don't, okay, so use that for p between 1 1/2, 1/2 1/4, 1/4 1/8, so kills another log, and you eventually end up with r square log to the 4th r. Of course, everything with probability at least 1 minus e2 minus some constant log cube. So this is the argument that says that the capacity is small. So again, there are 3 logs here to get 3 logs here, and another log from counting over scales with the probability. Please just ask anything you like. We have plenty of time, and I'm already done half of what I wanted to talk.
So I'm confused. You sum over P?
You sum over P, but of course in exponential scale. So you put here like P and P half or something like that. This argument works equally well, and that covers for you the capacity is the sum of escape probabilities. So I take this escape probabilities, I estimate individual. Okay. Any other questions? Okay, so let's go to the other argument, which is the other part of the argument, which is a version of a classical and very beautiful result for just random walk. So everyone who got confused by the previous part need not despair. because we are not going to show a classical argument for random walk, which you don't need to understand. Oh dear, I've run out of time. No, I kind of have a watch of my own. So, so let me tell you a classical result, which says that for random walk, capacity of A is always bigger, okay, bigger than some constant, depending only on the dimension, the volume to power 1 minus 2 over D. Okay, so this is just a result on random walk. Shh. Let me prove it to you. Okay, is the statement clear? Just simple random walk, dimension D, a bound of the volume given the capacity. Okay. Well, I think you will all agree, but D bigger than 3, that in D bigger than 3, A is equal to the sum of all points, the probability in the TIFR, that are exits A. Now, I'm not talking about escaping here, but about exiting. Not that it exits A at time 1, but it exits A at some time. But that's obvious, right? It's a transient process. So it exits A eventually. Okay. So let's break this sum according to the time and the place where it eventually exits. So we want that at time t it's at B, and this is the last time it's in the set A. Okay, so this is just I'm just taking the upper bound and broke it according to it's still an equality, not a bound, and broke it according to T and B. Now, of course, I'm changing order of summations. Now, of course, this is just the product of these two probabilities, right? We are talking about random walk. So random walk, this is the product of this probability and this probability. I'm changing order of summations, still an equality. Okay. And now the only part where there is an inequality is in estimating this sum. And this sum is just, you estimate it by the fact that random walk satisfies this. Do I need here time reversal or not? Yeah, let's time reverse. So you reverse time, and you notice that this is the same as random walk starting from B is a time t at A. So the sum over A for A. Okay, so now let's just bound only this guy. So I'm claiming that this is smaller or equal than the minimum of 1 and the size of A times T2 minus D. So the bound, this bound follows just from this bound. Because if the probability to be at any specific vertex is T2 minus D half, and you sum over the whole set, then this bounds this sum for a given T. Right, sorry, I'm only bounding the sum over A. Sorry, this is a bound over the sum over A, not over T. While on the other hand, because it's and the bound of 1 just comes because of it's a reverse random walk, so it should be somewhere. So the expected number of points where it is at the time t is most 1. Right? You sum this over t, you get A2 minus 2D, 2 over D, that's this is D function. You sum this over t, you get A to power 2 over D, move it to the other side, that's them. Questions about this classical?
Upper bound, right? You derived or
Yes, this is an upper bound. So
on the top?
here is the capacity, and the, if you want, it's a lower bound for the volume. Okay, any further questions? Okay, so by the way, I have no idea who proved that. I just read it somewhere and forgot and then remembered. So I certainly didn't invent that. It's classical, but I don't know who did steal. Okay. Okay, so this, okay, maybe I'll use the time, space over there. So the point is to, so the point of the proof is to replicate this proof for the one's capacity. And it's pretty similar. The only thing that actually changes is here where we use independence. Once is not really independent. Okay? Well, okay, of course, you lose an epsilon here also, but epsilon, no, you lose a 0.01 here also, but okay. But the trick here is what to do with this independence, and here you use this second assumption of relaxedness, because once you have lots of relaxed times, then you can in fact disconnect once reinforced from its path. So even though you cannot actually do it at any time you like for random walk, which is why we had that this is equal to the product of the two probabilities, you get that you can, after losing a little bit, after losing basically actually out. Ooh, I erased an important. I erased the end of H2. That's a bit sad. Okay, so. But you remember what was written here is that the probability that with high probability, you have lots of relaxed time at scale R to epsilon. So you lose this epsilon in the connection. But eventually, other than that, this is the only thing that has to be changed, this classical proof to make it work for the one's capacity. So what you get here eventually, so you get a similar inequality. So if there it will, so here you will get the one's capacity of A is bigger than A to power 1 minus 2 over D plus, I think maybe in the paper it's 0.06, not that anyone could care. What's the exact number? But a small number, the number that just depends on our assumption. Okay? And then so this is like 2B. And then you combine 2A and 2B to get that with very high probability. This is not a probabilistic statement. This is just a deterministic statement. It's not an event, just an inequality of things. And you get that the probability of the one's capacity of W intersection with lambda R. Sorry, not the one's capacity, not the one's, but the volume. The whole point, right? That's the point. That the volume is bigger than R to power 2 times 1 over 2 over D plus 0.03. Let's put 0.04 because to eat the logs is very large. What is it in there? The same estimate. Yes. Yes, sure.
Just a naive question. So if you are starting with the worst upper bound on the kernel, this
Here, you mean here?
yes, shouldn't you end up with the worst lower bound? Like, so you have
Did I make a mistake in the signs?
so this.
Yeah, it should be minus.
Yeah, thank you.
Thank you. Check. Yeah, okay, whatever, it doesn't say, but okay. Okay, and now you can see why we need 6 dimensions. Because, wait, no, it's over that. This is an estimate of the volume by the capacity, right? So it's, maybe actually that explains my mistake from previous. No, it doesn't actually. Now you see why we need 6 dimensions, why 5 dimensions is not enough. If we would do that in 5 dimensions, which is somehow the natural setup for these techniques, what you'd get here is 3/5 plus some error, which would give you a set of size 10/3, which is heatable in 5 dimensions. It's bigger than 3. So you will not be able to say that your past is not heatable. But if you're in 6 dimensions, so this is in dimension 5. But in dimension 6, what you get here is already 3. I think I didn't make a mistake, like 1 minus 2. Yeah, exactly 3. So if we would allow ourselves just a little bit of leeway, replace this by 3.1, then we would be able to make a proof. Because what you assume is what you need is stronger than what you get. So basically, the condition for making this argument work in the current shape is that this be smaller than, do not cross. Then, so the real condition here is that 2/1/2/d should be bigger than 2 minus d. And this only works in dimension 6 and above. Might have a few more minutes, but I think I said the really important parts. So maybe I'll end here.
Thank you very much, Gady. Any questions?
Yeah.
So by the history that you were telling, it sounds like the once reinforced is significantly harder because the linearly reinforced is much more studied, but it sounds like you're not changing too much. So can you comment on that?
The linearly reinforced has a special structure, which is called partial exchangeability. Basically, it says that, let me write that actually. So the probability that, let me denote it by L, linearly reinforced, is equal to some gamma. So this is just the probability. You have a gamma which is a fixed path, and you look at the probability that L actually traverses this gamma according to, in order, is depends only on the trace, on the trace of gamma. So what do I mean? It depends only on how many times gamma traversed each edge, but not in the order in which it traversed the edges. So trace here means just a set. Oh, well, okay, no, it's not a trace. But okay, yeah, let's call it a trace anyway. So it depends only on how many times you traversed each edge and not on the order in which you traversed it. This is called partial exchangeability. And it's linearly reinforced is the only reinforcement scheme for which this is true. And this is the main engine behind everything, all the research on this.
Any other questions? So I also have a question. So there are these kind of expansions for many models when the temperature is very close to infinity, for example, analyticity. So is there any way to quantify and get something like that?
We work with E2 minus log to the power for a reason. It will be significantly harder to get an exponential estimate. We are using the way that the first part works using the part that I didn't explain, how to get all these good properties of random walk, which are needed here. Yeah, well, I didn't also didn't explain why they're needed, but they are needed. It uses at some point Komlo-Schmeier-Tushnadi coupling. This is not so easy to get exponential bound of the kind we want for. No, it doesn't. It's not easy at all to get exponential estimating the probability in this technique. No, I don't. Certainly not easily. I'm not saying that there is. I don't see an immediate obstacle, but it's certainly not easy.
Thank you. Sorry, are there any other questions or? No? Okay. Let's thank Gady again.